This video will cover how to find limits for piecewise and absolute value functions, which we've been working with graphically, but this video will cover finding these limits algebraically. Before we get going, I want you to recall that a limit exists when the limit as x approaches c from the left of f of x equals the limit as x approaches c from the right of f of x. And this is just the formal notation way of saying that basically the left and right hand limits agree with each other or equal the same thing. And this is the approach we're going to use in this lesson today, since we don't have a graph to look at to evaluate these limits. So let's start with a piecewise example. So for the function f of x, we have 8 minus 2x if x is less than 4, and the square root of x minus 4 if x is greater than 4. So the first limit we're going to find in relation to this piecewise function is the limit as x approaches 0. So anytime we're working with algebraic limits, we're really checking to see if this number being approached by x is in the domain of the function. And luckily, 0 is in the domain of the function. So then the next step is, which of the two pieces of the piecewise will we use for it? And as you can see, for numbers less than 4, which would include 0, we're going to use this part of the piecewise function specifically. So once you figure out which piece you're going to use, I would prefer for you guys to actually rewrite that limit using that part of the equation specifically. So I'm going to rewrite this as the limit as x approaches 0 of 8 minus 2x, and from this point on it's pretty straightforward because we can just do direct substitution. So that would be 8 minus 2 times 0, which is simply 8. So for our second example, we're going to find the limit as x approaches 8 of the function f of x. So again, we check to see if 8 is in the domain, and this function has everything in the domain but 4 specifically, since it doesn't include that. So we know that 8's part of it. So then you figure out which piece to use, and since 8 is greater than 4, we're going to use this second piece of the piecewise function. So again, we're going to rewrite the limit, actually writing out the piece that we will be using, and then it's just direct substitution from there. So this is going to be the square root of 4, which we'll evaluate as a 2. So basically anytime the number you're finding the limit of is just part of the domain, you can pretty much use direct substitution and it should work fine. So what if we go for the obvious and try to find the limit as x approaches 4? Since from the left and the right, two different things are happening, we're going to have to use our formal definition here and actually see if the left and right hand limits agree. So for our third example, we're going to do the limit as x approaches 4 of the function f of x. So first I'm going to find the left hand limit, and if we're looking to the left of 4, that really is saying anything that is less than 4. So we'll be using that first piece to look at the left hand limit. Okay, so then the limit as x approaches 4 from the left of 8 minus 2x. And if we plug in that 4, we're going to end up with 8 minus 2 times 4, which is 8. And I'm getting a left hand limit of 0. So this is for our left hand. Now let's do the right. So as we approach 4 from the right, we're going to be looking at values that are larger than 4. So we're going to be using the second piece for the right hand limit. Okay, so now we're just going to substitute in that for the right. We'll be using the square root of x plus 4, and JK, that's a minus 4. And when we plug in a 4 and evaluate the function, we're going to get the square root of 4 minus 4, which is the square root of 0, which simply gives us a 0. And so that represents our right hand limit. Thus, since the left and right hand limits agree, we are able to conclude that the limit as x approaches 4 of the function f of x is 0. So for the second portion of the video, we're going to take a look at an absolute value example, since these basically become a piecewise function. First, let's recall that if we have the absolute value function f of x equals the absolute value of x, that the graph basically looks like this V shape that starts at 0 and goes up to the right, up one, right one, up one, right one, up one, right one, and it also goes up to the left, okay, kind of in an up one, left one, up one, left one, up one, left one pattern. Now, if I want to rewrite this as a piecewise function, okay, we're going to basically split it up into two parts, a left side and a right side. And this left side has a negative slope, it's going down to the right, and it has a y-intercept at 0, which we really don't have to put, and that's for x that are less than 0. Then for the right side of the graph, I have that positive 1 slope going up to the right, and again, a y-intercept at 0 that I don't really need to express. I can just put simply 1x. And that's true for all x values greater than 0. Now, 0 is a defined point on the graph, so one of these two inequalities should have an equal sign. It honestly doesn't matter which. I think a lot of people tend to put it with the greater than one, but it won't make a difference to what your answer is. So we're going to repeat this process anytime we come across an absolute value function, and we're going to turn it into a piecewise function so we can picture what's happening as we come from the left and the right. So let's try our next example. Find the limit as x approaches -2 of the absolute value of x plus 2 divided by x plus 2. Okay, so let's build our piecewise. So we typically like to go from left to right, so a lot of times the top row of your piecewise will be the left-hand side, and then we get to the right-hand side just because that's the way our x-axis goes. So to find the negative form of the absolute value, we simply keep whatever's in the absolute value in parentheses and just put that negative sign in front of it. Okay, and then the denominator was not part of the absolute value, so it's just a regular x plus 2. And this would be for all values that are below -2, or whatever makes this value equal 0. Just kind of thinking of the basic transformation properties, that plus 2 inside the function really moved the vertex left 2. So that, again, is why we're focusing as that being kind of our switch point between the two sides. Now, coming from the right side with absolute value is always really nice because it's just the positive version. You don't have to worry about anything new really being added, no negative signs. And that would be for anything to the right of that vertex. And then this time, I'm not actually going to put an equal with either of these inequalities here. And the reason it can't actually equal -2 has nothing to do with the absolute value part, and everything to do with these denominators of x plus 2. So the function can't be defined at x plus 2 because we would get, or sorry, at x equals -2 because we would get a 0 in that denominator. So now that we've built our piecewise, we can actually do our left and right hand limits. So the limit as x approaches -2 from the left of the function f of x is going to be evaluated with this piece of our piecewise. And the limit as x approaches -2 from the right of f of x will be evaluated with this part of our piecewise. Now, to actually evaluate the limit, if you notice, we can't plug in a -2. Direct substitution won't work. And we learned some different methods to try when this happens. And this one actually might be so easy you might not notice, but it's already considered factored. And we have that same factor on the top in the numerator as well as in the denominator, so they'll simply cancel out. So in reality, no matter what I plug in, this limit would just give me a -1 each time because those two factors end up canceling out. And similarly, when we look at the right-hand limit, again, we already have the same factor in the numerator and denominator that will cancel out every time, no matter what x we are trying to evaluate the limit at. And so this one would simply give me a positive 1 each time. So I'm seeing when I look at the limit as we approach from the left versus the limit as we approach from the right, when I look at both of them, they do not agree. And so because of this, we would say that the limit as x approaches -2 in general of the function absolute value of x plus 2 divided by x plus 2 does not exist. And again, the reason for this particular example was because of those left and right hand limits approaching 2 different values. So the only thing you might be asked that wasn't covered in a specific example is sometimes instead of finding the limit at a number, they might just ask for the left-hand limit only on a problem with absolute value or with piecewise. So just pay extra close attention. Are they asking for the limit as x approaches 4 or 4 from the right? Okay, because that'll be less work for you, so you're going to want to notice. But that covers everything for today's lesson, and hopefully you feel a little bit more equipped to handle these functions algebraically.